So for this module, we're going to be talking about gases and pressure units. So maybe this is a review when we were talking about solids, liquids, and gases, but gases have variable shape and volume. So if we think back to when we were talking about solids, liquids, and gases, solids have a definite shape and a definite volume. Liquids have variable shape, but a definite volume. And gases have variable shape and volume. So it's going to take the shape of its container, filling it completely, meaning if I were to blow up a balloon, that the gas isn't only going to blow up half of the balloon, it's going to fill up that whole balloon. And if it changes shape, the gas also changes shape. They expand uniformly. So the volume of a gas decreases when the volume of the container decreases. It compresses uniformly. So we know that a gas is constantly expanding to fill that container. It's not going to, if I had a container filled with gas, it's not going to just stay at the bottom of the container. It's going to fill, and those gas particles will hit the top, the bottom, and the sides. So it's not going to just stay in one small area. In your house or in a room, the oxygen gas is not going to stay near the window or the right side of the room, while the carbon dioxide is in another area of the room. So it's going to be uniform. Gases have a low density. So if you think about density, we know, like ice has a lower density than water because ice is floating on top of water. So density of gases, the density of air is about 0.001 grams per milliliter compared to density of water, which is 1. So 0.001 is substantially smaller than 1. Air is about 1,000 times less dense than water. And if you think about that, most gases are going to, quote unquote, float, right, or be above water. So yes, very low density. And gases mix uniformly, similar to that example I just gave, where my oxygen is not going to be in one part of the container while the carbon dioxide is in another part of the container. They're going to mix to form a homogeneous mixture. So, gas pressure is the result of constantly moving gas molecules that are striking the container walls. So, temperature is a huge piece here when it comes to pressure. If I have a high temperature, okay, that means that the speed of my molecules are very fast. If I have a low temperature, then my molecules or my particles are moving very slow. Kind of like if you think back to when we were talking about solids, liquids, and gases. In a solid, so think of ice, low temperature, so it's cold, those particles are just vibrating. They're moving very slow. As opposed to a gas, those particles are moving a lot faster. So now if we're just talking about gases, if I have a low temperature gas, those particles are going to move much slower. And if we increase the temperature, they'll move faster. Now, similar, and this is similar to the speed, but if you think about the force of the strike, so when these particles, and if you look down here at this example here, these particles, if they're moving faster because they're at a high temperature, if they're moving fast, it'd be like if you were running and you smashed into a wall, running really fast, versus if you're walking really slowly and run into a wall. Obviously, both are going to hurt and kind of silly, but if you think of the force of the strike, it's going to be a much higher force or a greater force when the temperature is high, when they're moving fast, versus a lower force when the temperature is low. And so the resulting pressure, so if you look down here, high temperature is equal to a high pressure. So resulting pressure is high. And then similar to over here, if we look down at this one, low pressure is directly proportional to having a lower temperature. So low temperature is lower pressure. So those are called being directly proportional. Now pressure, the definition of pressure is equal to force over area. And an example, if you look at this picture here where if you step on one nail, that's going to hurt pretty badly. If you think that the force exerted onto that nail is your whole body weight on one nail, that's a lot of force, right? But if you look at this bottom picture, the force, again, we have the whole body weight, but it's distributed amongst all of these nails, lots more nails, so a lot greater area. And so that pressure is because it's distributed, it's a whole lot less pressure. Now, I want to show you a simulation that will help to visualize this temperature and pressure correlation. So here's the simulation. There you go. We're going to add some gas particles into this container. We're going to wait a minute for them to reach equilibrium. So all of our particles are equally spread out within this container. And what I want you to notice here is that by adding these particles, and we can see how they are moving around, I have a pressure inside of this container of about 8.7 to 9.5. And that pressure is related to that force of striking on the container. And so what we're going to do is we're going to raise the temperature. So I want you to notice that the temperature here is 300 Kelvin, and I'm going to add some heat. What I want you to notice, here we go, add some more heat. So I went from 300 to 443. My pressure increased to now 13. Let's add a little more heat. Let's speed these particles up. Add some more heat. Notice I'm up to 762 Kelvin. So these particles are moving faster because of the heat. They are hitting the edge of the container with greater force, and therefore I have a higher pressure of about 23 now. Remember, I started at about 9. I can also cool it down. So down here I'm going to put some ice on this. I'm going to cool it down. What did I start at? I started at 300, right? We're going down to, let's get even lower than 300 here. Let's get down to, here we go, 182 Kelvin. So we're even lower. Look how slow these particles are moving. Notice they still are hitting the edges though. I mean, there is pressure even though I chilled it down. However, it's a pressure right around 5 to 6 atmosphere of pressure. What I can also do is I can look at this collision counter. So it's going to count how many times there are collisions on the walls of the container in 10 picoseconds. So let's do it at this 182 Kelvin. So when it's pretty cold, we'll start this. And there we go, we're at 40 wall collisions. But if I heat up, add some more heat here. Get way up. Raise our temperature, which is going to raise our pressure. All right, so we're at almost 700 here. And let's see how many wall collisions we have at this higher temperature. Here we go, we are at 81. So we can see more wall collisions because those particles are moving faster. So moving on to, we were just looking at pressure, and we could obviously see that as temperature increased, pressure increased. As temperature decreased, pressure decreases. And we could see that there was more pressure, more force on that container. So how do we measure this? Well, we measure pressure by using this barometer that was invented by Torricelli. And that measures atmospheric pressure. And what he found was that 1 atmospheric pressure, or 1 atmosphere of pressure, is 29.9 inches of mercury, or 760 torr. And what that was found, so they took this column right here, and they filled up this tube with mercury. And then they have mercury down here in this kind of a dish. And this mercury was filled all the way to the top. So even though there's a little bit of space up at the top, there wasn't. When they filled it up, it was completely full. And then they put it into this dish, turned it upside down, and some of it left because they found that atmospheric pressure left this little bit. So when they measured this, they took a ruler and they measured from here down to the bottom, and they found that on the ruler there was 760 millimeters of mercury in this column, and that is at sea level. Now, if I were to look at a ruler, 760 millimeters is equal to 29.9 inches. So that's where those two came from. So now we have a whole lot of other units that we can use to measure pressure. Similar to, looking at my ruler, I can use inches, I can use millimeters, I can use feet, I can use miles. There's lots of different ways. So knowing what we know here, we can convert from one unit to another. So here we go. We know that 760 millimeters of mercury is equal to 1 atmosphere. And that's also equal to 1 atmosphere is also equal to 760 torrs. Torr from being named after Torricelli, who invented the barometer. So we can then essentially say that 1 millimeter of mercury is equal to 1 torr. Then we also know that 1 atmosphere is also equal to 101,325 pascals. We know 1 atmosphere is equal to this many bars. We're not going to be using bars in this class. And we know 14.693 pounds per square inch, which is PSI, pounds per square inch, is equal to 1 atmosphere. So, and I'm going to write down this one, that this 1 atmosphere is equal to 29.9 inches. Hg is mercury, so inches of mercury. Now with that, we are going to do some practice problems, but first I want to show you a quick video about pressure. So this is a quick video about the history of the barometer. It's about 4.5 minutes long. So if you want to, if you're tight on time and want to skip forward, feel free to skip forward about 4.5 minutes. But I do think that there's some good information on it. So let's get started here.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
All right, so now that we have this history and background, hopefully you understand how this barometer works, we are going to do some conversions. Similar to the other unit conversions that we've done in the past, I want you to pause this and take a minute to try to convert. We know that barometric pressure is 26.2 inches of mercury. What is that pressure in atmospheres? And remember from the slide before, we know that 29.9 inches of mercury is equal to 1 atmosphere. So pause and take a minute to try to solve this problem. All right, hopefully you started with what I am asked to convert, 26.2 inches of mercury. Now we have our conversion factor right here. What goes where? Well, if I have inches of mercury on top, I need to have inches of mercury down here to cancel out, right? and remember also what I want over what I got. What do I want? It tells me I want ATMs. We know that 1 atmosphere is equal to 29.9 inches of mercury. So then we just need to plug it into our calculator, and my calculator will tell me 0.87625 atmospheres. But I need to remember significant figures. So if I look back to what I started with 3 sig figs. So I need to have 3 sig figs for my final answer. So that would be 0.876 atmospheres. And circle my answer. Okay, here is a real world example. Let's say I have a flat tire and I need to inflate it to 32 psi's. What is this in ATMs and what is that in millimeters of mercury? So again, if you can pause and try to set these 2 problems up. All right, hopefully you looked back on your notes to see that there was 14.696 psi's in 1 atmosphere, and because I have psi, I need psi down here to cancel those units out. So 32 times 1 divided by 14 should give me, my calculator would tell me 2.17746. And again, I need to look at how many sig figs I started with, which here would be 2 sig figs. So I need to have 2 for my final answer. So this would round to 2.2 atmospheres. Now, to get to millimeters of mercury, I can do one of 2 things. I could start with my 32 psi and go psi to atmospheres, but I already did that here because I can't go right from psi to millimeters of mercury. I got to get to atmospheres. So I'm just going to take this answer that I got from over here before rounding, 2.177, whoops, that's a 746 ATMs, and let's then do my conversion to millimeters of mercury. So looking back, we know that 1 atmosphere is equal to 760 millimeters of mercury, and I need ATM on the bottom for that to cancel out. So my 2.17746 times 760 should give me 1654.872. And again, I need to go back to what did I start with? And I started with 2 significant figures. So this would round to 1700 millimeters of mercury. So hopefully you are understanding the temperature and pressure relationships. Hopefully you are feeling comfortable with the metric conversions and with the introduction to gases and gas properties. Let's look at a couple more examples here. We want to convert a pressure of 635 millimeters of mercury into its corresponding values in units of atmospheres, bars, and kilopascals, kPas. So let's start with our 635 millimeters of mercury. And let's do atmospheres first. So what do we want? We want ATMs. What have we got? Millimeters of mercury. So we need to look at those conversion factors and see that correlation between atmospheres and millimeters of mercury. So if I look up here, you can see that 1 atmosphere, put 1 there, equals 760 millimeters of mercury. That's our conversion factor. So now I just need to do 635 times 1 divided by 760. And I should get 0.836. Again, millimeters of mercury will cancel out, and I'm left with atmospheres. Now let's do our 635 millimeters of mercury. Let's go to bars. What do I want? Bars, what have I got? millimeters of mercury. And again, if I look up here, I know that 760 millimeters of mercury is equal to 1.013 bars. Well, here I just need to multiply across. So I need to do 635 times 1.013 and then divide that by 760. And here I get 0.846 bars. And we've got one more, 635 millimeters of mercury. What do I want? Kilopascals, kPas. What have I got? Millimeters of mercury. And 760 millimeters of mercury is equal to 101.3 kPas. Again, I gotta have my units canceling, so I gotta have them diagonal from each other. So 635 times 101.3 divided by 760. Should get 84.6 kPas. Let's look at another example. At the summit of Mount Everest, which is 8,848 meters above sea level, atmospheric pressure is 0.29 atmospheres. Convert the pressure into its corresponding value in units of millimeters of mercury, bars, and kPas. So we're going to use those same conversion factors from up above, and I just simply want to go from atmospheres, what do I want? Millimeters of mercury to ATMs. So I'm just going to use this conversion factor, that there's 760 millimeters of mercury in 1 atmosphere. So I'm just going to do 0.29 times 760. So 220.4. This next one, bars to atmospheres. So I'm just going to use this conversion factor, the 1.013 bar for 1 atmosphere. So 0.29 times 1.013 to get 0.29 bars. And then last, I want to go from atmospheres to kPas. And if I look, the only place where there's kPa, I have kPas equal to millimeters of mercury. So let's get our atmospheres, millimeters of mercury, and then we can go millimeters of mercury to kPas. So actually, this is going to be a 2-step. We're going to go from atmospheres to millimeters of mercury, 760 millimeters of mercury for 1 atmosphere. And then I can go from millimeters of mercury to kPas. We know there's 101.3 kPas and 760 millimeters of mercury. So this is just a 2-step conversion. We went from atmospheres to millimeters of mercury, and then millimeters of mercury to kPas. So we're going to do 0.29 times 760 times 101.3 and divide that all by 760. We should get 29 kilopascals. All right, hopefully you're feeling good about doing the conversions. Take a second and try this one. If nitrogen gas has a pressure of 452 millimeters of mercury, what is that pressure in atmospheres? Pause the recording and do your conversion. And hopefully you got the answer of 0.595 atmospheres.